Hi, in this video, we want to take a look at transformations of continuous random variables. Okay, so the big idea here is that like when I'm doing like theoretical statistics, I'm doing proofs, I'm doing that type of analysis, I have a random variable, and for some reason, I want to modify things. I want to change things up because I'll get some other mathematical features that are desirable. All right, so when I do this, I need to proceed using some mathematics, specifically some calculus, some chain rule, or some U substitution, depending on how you want to look at it, is going to be super important for this. All right, so first one we want to talk about are linear transformations. All right, a linear transformation is where I just take my random variable and I replace it with something times a random variable plus a constant. So it's something like from a linear function from college algebra, similar to mx plus b, but here I have ax plus b. Okay, so if I apply this linear transformation to my random variable, one thing I would like to know is, what's my expected value? Well, I can tell you exactly what it is. So for any random variable with expected value mu, and for any real numbers a and b, the expected value of ax plus b is equal to, well, the expected value of x times a plus b. All right, so I mean, that's very nice. That's very clean. That's very easy. That's very simple. So if I go up and I have a random variable and I apply a linear function, you know, mx plus b type thing going on, I apply it to a random variable, then to get the expected value, I just plug in mu. Easy peasy lemon squeezy. All right, so why is this correct? All right, so now I'm going to show you the proof for continuous random variables, but this will also work for discrete. All right, so basically for discrete, instead of doing integration, we just do summation, and it's like butter. It's beautiful. All right, so the expected value of something, well, what I'm going to do is the expected value of a function is just the function times the density, then I integrate over the entire possible range of values. All right, that's just standard. All right, now I look at this, I see on the inside of the integral, I have a parenthesis times a function. Well, what I can do, I could distribute that f across the parentheses, so I know I can take the f, go ax times f, b times f, okay. Now I remember that when it comes to integrations is what's called a linear operation, in that I can break this up across the plus sign and I can factor out that a. All right, so what that does, I look here, I realize that, hey, this part right there is actually the expected value of x. Well, that's mu. Boom, I got mu. And then here, that's just a times the integral, it's a times mu. Now here, when I look at this, I realize that that is integration over the real line of a probability distribution function. Well, probability distribution functions have to integrate to 1 because it's a probability. Therefore, I know what this integral is. It's 1. Boom. So b times 1 is b. Bam, we got our result. Okay, so now let's kick it up a notch. So we looked at what's going on for the expected value. Let's take a look at the variance. Now, the variance is a little bit surprising. I was surprised by this when I learned this. For any random variable x with variance sigma squared, if I apply a linear transformation with a and b like this, the variance of ax plus b is a squared times sigma squared. Now, the thing that surprised me about this is that b is not involved. Okay, so if I add a constant number to a random variable, if I add a constant number to data, that does not change the variance. Okay, but multiplication does. So if I multiply by a, then the variance gets multiplied by a squared. Now, if you stop and think for a moment, remember that variance is on the unit squared. It's not on the same scale as the original data. So if I look at this for a moment, I'll realize that if I'm concerned with standard deviation, what this is going to be the standard deviation of this transformation of the transformed random variable is going to be the absolute value of a, because we take a square root of something squared, absolute value, times the standard deviation of the random variable. All right, no, so why is this correct? Okay, so what we need to do, we need to take the variance, and so we're just going to use the definition. I'm going to take the random variable minus its expected value, square that, then multiply by the density, take the integral. So I take the random variable, I subtract its expected value. You notice that there's a mu right there. I square the whole thing. Then I multiply by the probability density function. Then I integrate over the entire real line. Okay, so basically all I've done is a definition of variance at the step. Now I look at this and I realize that I have ax plus b. Now negative sign I can distribute. So it's negative a mu, negative b. Well, the b's are going to cancel out. Boom, I have ax minus a mu. Now, I look at this and I go, hey, I could factor out that a. If I factor that out, it's going to end up getting squared. But wait, there's more. I can factor out the integral also, because we can do that with the integration. So the a squared comes out front. So now I have x minus mu squared times the density all integrated over the entire real line. And I realized that, hey, that's the definition of the variance of x. So I just put the variance of x in for that integration. Boom, I've got the result. Okay, so now it'd be reasonable to go like, why do I care? Why would I do this? Well, believe it or not, I use this a lot at work. How do I use this at work? Well, one thing I like to do is to standardize the data that I'm working with. So here we're going to be instead we're not standardizing the data, we're standardizing the random variable. There's a direct relation there. So if I have a random variable with mean mu, standard deviation sigma, then this fraction here has mean 0 and standard deviation 1. Why do I like that? Well, that standardizes the entire random variable. So if I had multiple random variables and I standardize them to have the same mean of 0 and standard deviation of 1, it makes it easier to compare them on certain properties. And also this can make a lot of other mathematical properties nice to work with. If you're doing proofs a lot, this is a nice type of random variable to be working with. All right, so here what's going on is that a is 1 over the standard deviation and b is mu over the standard deviation, but negative. All right, and so then I have everything that is coming up from the previous thing about expected value and variance comes to bear. If I run through this, we'll see very quickly that we will have mean 0 and standard deviation 1. All right, now another one that is useful a lot. So this one, the one mean 0 standard deviation 1, that's frequently used in statistics. Now, if I'm doing machine learning, a lot of machine learning algorithms like to have things from 0 to 1. So here the minimum value of 0 and the maximum value of 1 is highly desirable frequently. And so here we're standardizing the range of values. So if I have a random variable x with a maximum possible value and a minimum possible value, then if I take this random variable instead, then automatically this is going to have a minimum value of 0, a maximum value of 1 possible. And so here we've standardized the range of our data, a range of our random variable. All right, so now let's make it a little bit more complicated. So here, everything I talked about was similar to a function like mx plus b from college algebra. Now let's kick it up a notch. Let's start looking at something more similar to calculus. All right, so let's say I have a random variable x, and we have a strictly monotone function. It's either always increasing or always decreasing. For this moment, doesn't matter. And let's say that u is the result that I get from plugging x into that monotone function. So we say that u is equal to h of x. Now, it follows that x is equal to the inverse of h times u. All right, now remember that because it's a monotone function, here we're saying strictly monotone, so always increasing or always decreasing, then the inverse automatically exists. All right, so now let's think about the cumulative distribution function of u. All right, so if u is equal to h of x right here, so x is a random variable, u is what I get from plugging the random variable into a function, then the cumulative distribution function of u is equal to the probability of u less than or equal to a given value. All right. Well, I replace u with h of x right here. Okay. So now I see that h of x is less than or equal to u. Now I remember that h is a strictly monotone function. Now here I'm going to go ahead and make the assumption that it's strictly increasing, by the way. The modification is very small if it's decreasing. And so here I apply the inverse to both sides, like that. And so I can see that the cumulative density function of u is equal to the cumulative density function of x, but on the inside, I put the inverse of the value that I'm concerned with for u. Okay, so here this gives me the ability, this right here gives me the ability to go back and forth between cumulative distribution functions for between an original variable and a variable that comes from a transformation. Now, let's see if we can modify this. So this is the cumulative distribution function. Now I want the probability distribution function. All right, so for the probability distribution function, remember, I have to take a derivative of the cumulative distribution function. Okay, well, when I take the derivative, I'm going to need to use chain rule, because you'll notice I can take a derivative of this on the left. That will be very easy. I'll get f of u. Over here, you notice I have this h inverse on the inside. All right, so what's going to happen is that I'm going to have to use chain rule, or equivalently u substitution, to accomplish this. So here, when I have this particular relationship between u and h is strictly monotone and differentiable, then the probability distribution function of u is equal to the probability distribution function of x with h inverse on the inside times the absolute value of the derivative of x with respect to u. Okay, so how do we prove this? Well, what do? I start with the result we have for the CDFs. Now I take the derivative of both sides with respect to u, and on the left I have the probability distribution function of u. Okay, so the left-hand side I'm done with. Now the right-hand side, I look at this and I go, wow, I've got an x and a u going on. That kind of makes me remember like something like with chain rule. So I'm going to go ahead and use chain rule. I know that I can go about this by changing this to the derivative with respect to x on this part, and I change this to x, be consistent. But remember, I have to, by chain rule, pull out this x and take the derivative with respect to u, and boom, I've got that. So now I have that f of u is equal to f of x with x on the inside. Notice that it is a different variable that'll be important for calculations, times the derivative of x with respect to u. Okay, so now I've got a variable here that I don't really want. So because I want u, not x, so I'll go ahead and make the conversion. Now, when working with this, if h is strictly positive, then this derivative is going to be a positive number. Okay, no problem. Now, what if h is strictly decreasing? Well, this derivative here of x with respect to u will be negative. But that doesn't really make sense for the purpose of integration and probabilities. So I'm going to go ahead and make it positive with an absolute value. And so just to make the formula a little bit cleaner, we're going to put an absolute value bar on this. That way I don't have to think about, is it positive or negative? Is it increasing or decreasing? Now, something about this. When I work with this, I need to express the derivative of x with respect to u in terms of u. So this is an important point if you're going to be using this, is that this dx du, I need to write it in terms of u, not x. So I'll need to use like an inverse function or something like that. All right, so that is transforming variables. I've got gnats in my face. I need to mow my lawn. All right, so here, so let's go ahead and let's make this a little bit more concrete. Let's apply this to data. So there's some transformations that we use a lot in statistics. First one is center and scale. Second one is log transform, square root transform, range transform, and then power transform. Okay, so center and scale, what this does, this sets it up so that my data has sample mean 0 and sample standard deviation of 1. And to get this, I want to use the scale function in R. So this is the base R version of it. There are other versions and packages, but I find that this is just good enough for everything I do. Some people like slight variations from other packages. So this is nice because when everything has the same mean, same standard deviation, it's easier to compare things. Also, it makes some inferences easier to reach. The next one I want to look at is the log transform. To do this, I use the log function in R. All right, so if I have highly right skewed data, which we frequently have whenever we're dealing with money, some aspects of statistics don't really work out well with highly skewed data. For example, regular means, like sample means, do not really perform that well when I have right skewed data, heavily right skewed. So what I'm going to do, I'm going to take a log transform and I'm going to treat that as my data. So I go log of my data. Now, by default, the base of the logarithm is E. Base E has the most nice mathematical properties. So if you want good mathematical properties, go base E. Now, if I'm working on a project, let's say I'm working with scientists that use scientific notation regularly, I'm going to go ahead and use base 10 because that is very natural for what they're doing. And because ultimately when I'm doing statistics, my job is for communications. And I need to get the people that I'm presenting to buy in on my results. Now, if I'm doing something like with computer science, I'm dealing with binary a lot, then I'll go base 2, because that's very natural. Now, the square root transform is another one that we frequently use, and that is with the square root function, SQRT function. Here, this is frequently used when I have count data and I'm performing regression. So there's some theoretical results in regression that shows that we like to have certain properties going on. And square root transform on Poisson distributed data has closer to those properties than the regular data, the untransformed data. Now the next one is the range transform. And for that one, we use the rescale function in the scale package. What this does, I use this to change what the maximum and minimum values of my data are. Now, this is a linear transformation, just like we talked about at the beginning of the video. Now, the default is to put this on 0 and 1. This 0 to 1 data range is very common when I'm doing machine learning. And so if I'm doing machine learning with certain functions, certain algorithms, I will probably want to apply this to my data before I start running the algorithm. Now, the next one, this one is a doozy. It's a little bit more complicated. These are power transforms. And the version I'm going to show you is from the car package and is the power transform function. What this does, this function works to find a transformation that makes the data less skewed and look more similar to normal. All right, so we have three options: Box-Cox transform, modified Box-Cox transform to accept negatives, and then Yo-Johnson. All right, so the Box-Cox transform can only take positive values. And the transformation is I take a parameter that is the power of I take my data, put it to the power of that value, then I subtract 1, and then I divide by the parameter. Now, something about this, if you look at this from a calculus and limits point of view, when lambda is equal to 0, this is equivalent to the log transform in the limit. So if you take the limit as lambda goes to 0, you get the log transform. Now the next one is the modified box-Cox transform, and to do this one, we set the family parameter to BC in power. And what this does, this allows negative responses in our data. So we have negative data in here. Now the Yo-Johnson is similar to box-Cox, and it allows a few negative values. All right, so now for your assignment for this video, what I want you to do, I want you to take some data that you're interested in, and I want you to do some transformations. So first, I want you to take some numeric data that interests you, plot a histogram. Call it raw data in the label of your histogram. That way I know which one it is. Now, I want you to take that data, I want you to center and scale it, then do a histogram. Label it, center, and scale. Tell me what is the difference between your raw data and your centered and scaled data. Next, I want you to change the range of your data to 0 and 1. Label it, rescale. Then tell me, how is your data different? Next, apply a log transform. Now, if you have negative values, 0 or negative values in your data, you will not be able to apply a log transform. If that's the case, use the rescale function to change it up so that you can. And tell me, how is your data different? This one should look very different from the original data. Next, I want you to take the square root transform and do a histogram. Now, if you have negative values, use the rescale function appropriately first. And then last but not least, I want you to do a power transform. And go ahead and use the car power transform function and give me a plot and tell me, how is this different from your original data? And comment on how your data has changed, and label your histogram with the parameter you use. So it's either going to be BC power, BC in power, or Yo-Johnson power. That's all I've got for you. Take care and goodbye.